Our next session in the ST2110 Launchpad series is on networking, specifically how to design an IP network to support ST2110. And I'm very pleased to welcome Martin Walbum, who is the Senior Vice President of Solution Strategy for Nevion. And he should be able to give us some really good insight because I know Nevion's built a lot of these networks and looking forward to this. Thank you, Martin.
Thank you very much. Hello. I'm going to take you on a very short journey into how to design IP networks for ST2110 and what to consider. Of course, 25 minutes is just scratching the surface on such a topic, but we'll try to give a brief overview of that. So, before we go into trying to design anything, we need to know what we need to design it for. So an IP network is many things. There's one big trend that has been going on for a long time is this convergence between wide area networks and local area networks. And we're actually designing 2110 networks for both and also for the combination of the two. So before we start designing the networks and deciding how the architecture should be, we of course need to know where are we? Are we only designing for a local area network? Or will it potentially at some point migrate or merge into a wide area context? So that's very important to think about things a bit upfront. What are we going to do with this in the future? Another thing that I always try to zoom out a bit and say, well, what's the purpose of IP? We're not just introducing it for the fun of it. There needs to be some kind of purpose of this. And the purpose that we are seeing with IP networks is really around sharing of resources, sharing of processing resources, better sharing of people around, locations, and even going into possibility of moving and into other types of services in the future. And IP as a common transport mechanism enables that. Wes mentioned earlier that when you move into 2110, you are not as dependent anymore on the different formats that you are having. It's more flexible for that. You don't have to swap your infrastructure all the time. But it requires that you think a bit about what are you going to use it for? What's the end game here? So now that we have thought about that, let's see what is the measuring point for creating a successful network. What is it once we're done that will make us say, ooh, this works, or ooh, this is not very good? And the measurement point for many of our customers in the broadcast industry is, of course, where we're coming from. So we used SDI infrastructures, which is dedicated infrastructures for transporting video, of course, audio infrastructures as well for audio. And they have some prerequisites that we've gotten to very used to and to like very much. It's media-centric, so those types of infrastructures are very dedicated for one particular application. They're very high performance. We have deterministic routing, so we know exactly where signals are going. We can even follow signals through a cable in a direction, only one signal per cable. That's where we are. And if we need to switch between sources, it's very fast and seamless. That's the measurement point we're trying to do. And now we're trying to move into a packet-based network, as it was explained earlier. All of the different content we have is being broken up in different packets, whether it's audio, video, the data part of it, it's all broken into small packets. And we are now trying to run those on top of an IP network that is packet-based. Now, I put here, it's a high-performance IP network. So we hear this all the time. I need a high-performance IP network. So what is that? It depends, again, on what you're measuring on. What are your measurement points for high performance? And that is, of course, dependent on the application that you're putting on top. So if we look at that, we can see that there's a number of things that we can measure on and which are true in the media and broadcast space. First of all, we've got very high volumes of data. As it was said earlier, we are here typically talking about uncompressed videos. Uncompressed UHD is 12 gig per second that we want per stream in these networks. We want it to be extremely low latency. We don't want long latencies in the workflows that we are used to. It needs to be very short. We need to be able to switch between signals, switch the setup very fast, very frequently, every time we go to a new type of production or we need to do live production. We cannot tolerate failure. There has to be redundancy in here, and always up notion is brought in, so we have to think redundancy in here. All of these come together and then actually look as very demanding. But if you go out to people designing other types of networks, I've been designing networks for stock exchanges, for instance. They would claim that that is pretty sensitive networking as well. And then they would also tick all of these boxes, but in a different way. So that there are differences in the way that this is, and in the measurement points, and in the way the traffic behavior is. And then that's what we need to think about. So what are some of the specific challenges for media networks, and specifically for 2110? Well, I would like to highlight 4 main ones here. I put here as the first bullet, it needs to be very dynamic and scalable. We've been building a lot of networks, large ones, small ones. All of them have been growing and growing much more than it was anticipated in the beginning. So when embarking on a journey in IP, you need to make sure that you create a system and an infrastructure that is scalable, so that you're not locked into an architecture that is limiting in its own term. That's very important. The amount of multicast flows that we're dealing with here is quite exceptional. In a normal or classical IP environment, multicast is not that used. Here we're talking about multicast with very high bit rates, traveling on the same network as multicast with very low bit rates. And we have to be able to balance the traffic across the network in order to have a decent use of the network as well. As we heard in the last presentation, PTP, mission critical. So we need to make sure that we select network and design the network so that PTP works, also with the redundancy aspect of it. Now, the question we often get when people embark into a new IP media network is, so it's IP. I have multiple IP networks in the environment already. There are sometimes people have been building playout systems. There's of course the office network for file-based applications, for telephony, for all that stuff. There's maybe a network for management traffic to handle network management. There's the data center applications, and then interfaces into wide area networks. So can't we just take our 2110 traffic and put it on top of some of those networks instead? Why would we think of building a new one? And that is actually a good question, and it again depends what the purpose is of things. Typically, we would say that for these real-time media applications like 2110, we would build a separate network for that to handle that. You could probably collapse a lot of these, but the thing is that the needs for each of these is very different. So if we, for instance, compare an enterprise, classical enterprise network, where you put your telephones, your PCs, your Wi-Fi hotspots on, that is typically unicast. It's not that high capacity on the interfaces you need. You don't need 25 gig interfaces to attach your PC. It's typically only data. It's TCP from a transport protocol perspective, and you don't really need the timing. And you compare that with the live broadcast networks that we're talking about here, where you have a mix of different audio, video, data applications. The interfacing can go, yes, 1 gig is plenty to attach an audio device, but it's not enough to attach a video device. So you have a very big span. And then if you were to say, well, let's collapse these two networks and run everything on the same physical infrastructure, you could probably do that, but it would be very expensive because you would have to tune both sides to have a common denominator that's very high that fits both of them. And therefore, we see these networks as being split in their nature. So it does not make sense to combine them. Okay, so how do we design these networks? How do we build the architecture? And again, it depends where we are. There are many, many different types of architecture you can think of. And I'm going to go through a few of them here just to have some of the options and pluses and minuses for each of them listed here. So you can build star topologies. We heard the term leaf spine earlier on. That also comes in a few different flavors, by the way. If you go into a wide area, doesn't even have to be that wide. Sometimes we have customers that have a campus with multiple buildings. Well, there you are maybe sometimes dictated by the way the fiber is laid out. Could be a ring between buildings. So we need to be able to then design and architect the network so that you can fit a ring into it as well. We don't know what's going to happen next year or 2 years from now. Maybe we can benefit from putting a triangle in or whatever. So thinking about this up front, what could the needs be going forward, is very beneficial to have an infrastructure that can be lasting for a long time. Let's look at one of them. This is the one that is typically called monolithic approach. It's a very used term. So you have one switch that you put in, and you hook all your stuff up to that one switch. You can't really live with that because we're talking about the term of redundancy. So you need to put another switch in. So you now have your red, blue. It's just two switches. They are isolated, separate. I would claim, as a network engineer, that's not really a network. It is an IP device, yes. But a network only occurs when you start having multiple devices put together. So this is not really a network. The advantages of this is, of course, it looks very much like the topology we're coming from, if you compare to SDI. It looks like the big MCR SDI router, one big thing where everything comes in and out. It is non-blocking, if you pick a switch that is non-blocking, by the way. And you don't need any special technology to route here and tell the traffic where to go. It's fairly simple. Thing come into the switch, can come out another port. It has its challenges. It's the fiber management, for instance. If you have a huge switch you put in the basement, all the fibers coming from all your devices, they need to be attached to that single switch. That's a lot of fiber management you need to do. There's no aggregation of your traffic there. So not very well used fiber either. So fiber is a scarce resource. But the bigger challenges are probably around redundancy. If you want to have redundancy, it has to be handled at the edge of the network here, like I'm showing on the video switcher icon there, where you have to dual home in. And if you have devices that only have one interface, how are you going to build redundancy here? There's no network redundancy here inherently because there's no network. So those are some of the challenges there. Unfortunately, we see a lot of people getting their toes wet in the 2110 by saying, well, let's test if this works. Let's see how it works. And focus is, let's get a camera, let's get a multi-viewer, let's get a server and put it together and see how that can play together. And we get all of that stuff in, we need an IP network. So we get a switch, we put it in, and then we try it out, and it works. We've seen it quite a lot of times. And then people start building like that. But they haven't actually tested what happens when you start moving into a situation where you have more than one switch? What happens with the load distribution of the network and so on? So I encourage to think a bit further and think about the fact that one switch does not scale very far. You would need more than that in the network. So the next option is one that is typically called dual star. We can also call it, it's a red-blue network, completely separate networks. This is something that a lot of people are considering to build. It's nice from a redundancy perspective because it's completely isolated, two isolated networks. There's the red one and the blue one. We still have the issue of the redundancy being at the edge, right? Because every device attached to the blue network has no attachment to the red network unless it has two interfaces on it. So it's very separate networks, but this is the way that a lot of people work. Some of the fiber management is solved here because you now have switches on the front that aggregate. So you now aggregate more signals before you go up to the central switch. We often see this referred to as a leaf spine network. So the big switches on the left here, you call the spine switches. And then you have the leaf switches on the other side. So this is a two-layer approach, but it's not what we call a true leaf spine environment. It's a dual star, and it's important to understand the difference of that. Because every leaf here is only attached to one of the spines and not to both, which also means that there's no built-in network redundancy here. If I lose a spine, well, then I lose all of the devices and traffic that runs on that particular spine. And if I'm not in a situation where all of the end devices have two legs and are attached to both, well, then I lose some of my capacity. So another way to do it is what I'll a bit bluntly call the true leaf spine. It's also referred to as the purple network, where the other one is the red-blue or amber-blue network. This is the purple network. And the purple network, the rule here is that all leaves are attached at least once to every spine. And I deliberately say every spine because here I'm only putting two. But the benefit of this solution is that you can very smoothly migrate it. So you can add another one. So you add a third spine. All it requires is that you then have an uplink from each of the leaves to that third spine, and you have added capacity. You can have a fourth one. We have customers that are running with 8 spines. So, and then you can distribute the load across. So you have aggregation of your traffic here, and that benefits you from that. So you have better use of the fiber here. Some of the challenges here, when you look at this, it becomes a web of connections. So how do you handle that? There is an issue that pops up when you look at an amber network, a purple network, with how do you route your traffic? How do you ensure that you know where your traffic is going? And how do you ensure that these links are not blocked by the routing protocols used blocking links because there's loops in the network? That typically happens in classical IP networks. So we typically say that this is a very scalable way to build your networks, but you need some kind of orchestration sitting on top in order to be in control of what's going on and in order to load balance your traffic across all of this infrastructure. Of course, when I start adding a third and a fourth spine, then you start getting a lot of routes around the network to actually balance your traffic. Some say, well, I'm a bit nervous here because this very nice notion of having a red network and a blue network separate, if one fails, the other one is still there. I don't have that anymore. So what happens if something fails? Important to understand here is that I still have the red-blue transport in here. So as you can see, because every leaf is attached to every spine, my traffic can still go in 2 different directions. So my red-blue redundancy is now on a signal by signal basis, and I can choose if I want to distribute the traffic across 2 spines or 2 routes or only on one. And then I can do my 2022-7 protection switching, as we learned earlier, on this particular session. Again, I need some mechanism to enforce this so that I'm sure that the red and the blue don't go across the same spine, both of them, because then it doesn't help me. So that's why we typically recommend to put an orchestration software of some kind on top of this in order to manage the traffic that's going across. And that brings me into the traffic control, because that's an important part of designing a network also. Deciding how is my traffic flowing in the network, and who decides where the traffic goes, especially in bigger networks, that's important. If you have one switch, so not a network, then it's easier than if you have a big network. Now I'm showing some networks here that are a bit more meshed and larger, but we have 2 main mechanisms for routing signals in a network for multicasting. One I call automatically routed network. That's the classical way of routing traffic in an IP network. This is where the intelligence of the routing really sits in the routing tables in each and every device, each and every network switch. So there's a routing table, and the way that routing table is populated, the routing table tells for which traffic, where it should go from each and every network element. So that intelligence sits in each element its own, and they communicate together via routing protocols to find out what the best path is in the network. And that communication is typically done based on the core configuration of the switch. So the initial configuration, some network engineer sets it up based on knowledge about where's the traffic predicted to come from and where is it going. And then we build the routing tables like that. So there's certain dynamics there, but once it's set up, you typically have that set up in the way that it is. On the other hand, you've got what is called software-defined networking. Software-defined networking, you take the intelligence out of the network and put it in a central place. I typically call it the GPS or sat-nav of networking. So if you go out and buy a car, very nice car, drives fast, doesn't really help you if you save on your sat-nav and you are stuck in traffic all the time because you're not guided in the right directions there. You can buy your sat-nav, but if you save on the traffic information system there so that you don't know when there's a congestion anywhere, well, you know where the shortest route is, but you will not get routed around the traffic jams that are there because you don't have that functionality. It's the same here. A software-defined network takes a holistic approach to route calculations, and every single time you set up a route through a network, it will be guided and routed through and around issues in the network, around failures in the network, and so on, and can also balance the traffic based on information about where traffic is currently at in the network. So you get a better utilization of that. You can argue that if you only have one switch or a very small network, that may be overkill on one side. But again, remember that when you're starting and embarking in an IP environment, it's very likely that it will grow in size. It's not just one switch. You buy a switch to attach video components, you find out, 25 gig ports, kind of expensive to put a microphone on. So why not put a small gigabit Ethernet switch behind it to then aggregate all of your audio devices? Now suddenly you have 2 switches and you have a network. So you need to upfront consider how do you then treat that network and how do you route traffic in that. This is a very big topic on its own. I just wanted to touch on it because it has an influence on how you design the network and which of the designs and architectures you pick that I showed before. So how do you pick the right switch for your purpose? Well, it really depends on the actual application you have. It depends on the size of the network you're trying to build. Is it a local area network? Is it a wide area? Is it a mix of those? And are there any other features that you need in here? Because there's some certain basic things like PTP that needs to be there. I put it in the last one there. Either boundary clock or transparent clock needs to be there in order to have a properly working 2110 network. And of course, you need a switch that doesn't block the traffic. So it needs to be a certain performance. But when you start building, there might be other things that you would like to add in for convenience to be able to scale better. And I just mentioned a few of them here. I'm not going to go through all of them. To indicate that when you look at these switches, there is a reason why there are different switch vendors out there. They each have different additional functionality. They have different scaling. PTP, by the way, is also important to find out how many PTP clients can you have on that switch. If you run a small network and you run all your clients off one switch, well, we've seen switches that support PTP, but there are only a few clients and you run out of them and you can't scale anymore. That's an annoying way to not be able to scale and have to swap out your switch because you saved a bit on the switch. So these are just some of the factors to count for when designing the IP network. I hope that gave a very short introduction to this. Ready to take a few questions if there are any on this topic.
You guys don't really make switches, right? You just help people specify them. Is that correct?
Yes, that is correct. That is true.
Yeah, so you have a chance here to get an agnostic view if you'd like. So. Okay. Thank you very much, Martin.
Thank you.